Okay, so we can start the session, guys. I think this is going to be the last lecture or last session for the ROS 1 course. And yesterday we have been discussing about the state machine. We just started with the state machine, and today we will be seeing an application of the state machine. Only that. Okay, so we will be discussing that application. Mainly it is related to the navigation of the robot. Okay, we will get back to that. So we are discussing about the Smash state machine library. So we will be seeing how to create a real life application, robotics application using the state machine. So this chapter is actually based on the book actually called ROS Robotics Project, one of my book, second edition, but this chapter actually contributed by another author. Okay, so what we are going to see today is we are going to see the restaurant delivery robot application. So yesterday I think if you attended the session, you may have seen a scenario in which we can use the state machine. Okay, so if you are not aware of the state machine, it's simply a sequence of states. State means, like, for example, if you give an order, the robot will do something. If the order fails, then it will do something. So based on the inputs, it is doing some task. That is what we are called states, and the state will have output. Okay, so if the robot is going to deliver the food, it will have two outcomes, right? Like it can fail or it can be successful, like that. So so state machines will help you to sequence a set of tasks and connect these tasks. So whenever the robot do a task, after doing this task, it will have an outcome, and based on the outcome, it will trigger another task. Okay, so that is what the state machine's all about. It is very helpful for creating robotic application, mainly to sequence or orchestrate, choreograph all the robotic applications. Okay, so this is one of the basic state machine example. Maybe I can show you that, just a second. Yeah, so if A is a task, after if it is complete, okay, if A is a task or state, if it is complete, it will have two outcomes. Either it will success, otherwise it will fail. So success indicates 1 and failure indicates 0. So if it is success, it will be going to B, okay, task B or state B, and the B will be started working, and if the B is successful, it will go to C. Okay, and if C is successful, it will be going to D. So yesterday, if you remember, I have shown you the example of this simple state machine simple state machine. Maybe I can show you that, so you will get a clarity. So let me run the first example to get an idea before starting with the actual application. So yesterday we have been discussing this thing, like we have started that state machine, and this is what happening. Okay, I can show you that. So this is the visualization of the state machine. Okay, so we are working on a state machine library called Smash, and the Smash will help you to create state, and we can add these states to the state machine, and we can start it, and we can also visualize or introspect. I hope you remember RQT, right? So using RQT, we can debug the ROS computation graph, right? So similar to that, you can see the state machine, the current state of the state machine. For example, the green indicates it is going from one state to another. Currently it's B, then C, D. Okay, so we are giving an inputs to A. Okay, so if the input to A is 1, then it will be going to B. Okay, then if B is successful, it will be going to C. So you can imagine it's like a choreographing of robotics tasks. Like if you are doing a complex robotics application, you may require these kind of techniques to sequence your task. Okay, so this is one of the simple state machine, and yesterday I have discussed the code as well. You can find the code here. So simply like there is a library called Smash. We can include that in our Python code. By the way, Smash is a Python based library. I don't know like whether we can code it in C++. So we have to write a Python ROS node, and in this library, using this library, you can define a state, okay, state as a class. So you can see class A is actually inheriting from state class. Okay, so that is what we are seeing here. Then there is class B, class C, and class D. Okay, so that is what we are seeing in this diagram. Like we are actually implementing state A, B, C, and D. Okay, so state A or state means it is actually a task. Okay, for example, a state can be detecting an object. Okay, so detecting an object. So what is the outcome of the state? It can be detected or not detected. Similar to that, we are saying A is a state machine, and which is have an outcome 1 and 0. Okay, so we can decide the state or we can decide what is happening in the state and what is the input and output. Okay, so that is what we are seeing here. While creating the state, we can mention the outcome, and we can also mention the input. Okay, and whenever the robot comes to this state, it will be start executing a function called execute. Okay, so whenever this state B reached or state A reached, it will call an execute function, okay, by default, and inside that we can do whatever we want, detecting an object, then moving the robot, whatever we want. So here inside this state, what is happening is that it will check the user input. Okay, if the user input is 1, okay, then return 1. Okay, return outcome 1 or 0. Okay, so I will be showing like how can we give the user input. So this is what we are seeing as a state. Okay, there are 4 state, and this is what we are creating the state machine. So I hope you remember the difference between a state machine and state. State is actually the individual task. We can say A is a state. Okay, so if you combine all the state, like we can say it's a state machine, or state machine is the combination of all these states. Okay, so we can construct a state machine by adding the different states. So that is what we are seeing here. We are creating a state machine using this line. Okay, there is a class called state machine, you can see here. Okay, from Smash library we are importing state machine, and we are giving the user input as 1. Okay, so it will be going to the first state. Okay, you can see here the first state that we are including is A. Okay, A is the first state. So user input to A is what? User input to A is 1. Okay, and this is how we can add states to the state machine. Okay, so we are adding A state machine, and we are naming the state machine as A itself. We can name it, actually we can give any name. So, and you can define the transition. Okay, we can define the transition, and also we can define the the remapping. So if you want to give some remapping of the input or something, you can give here. So what is happening is that like if you see transition 1 to B, 0 to D, that means if the state return 1, okay, it will be going to B state. That is what we are seeing here. If the state A return 1, then which is the transition? Transition to B. But what about state returning to 0? Return 0, that means it will be returning to or go to D. Okay, so the state transition is actually giving here. Okay, and the input name is actually given here. So if you check the state class, we can see input key, name of the input is input only, right? So we are just remapping the input to SM input. Okay, that is what we are meaning the state machine input. Okay, and output to the input. Okay, so the output of each state machine will be the input of the next state. That is what it means. Okay, so so basically these are the 4 states, and then what we are doing is after adding this state, we are starting the introspection server, meaning we can see this graph, right? How the states are switching. So in order to get this graph, we need to enable this thing called introspection server. Okay, introspection server, and then we can start the state machine and it will be like running. Okay, so basically we have to define the state. So these are the basic hello world state, we can say, and we have to add states to the state machine, and we have to start the state machine and the introspection server. Okay, so this is what we have discussed yesterday. So now we are going to the actual application of this. Okay, so that is what it is mentioned in this chapter. So I'm just taking that example. Okay, I can quickly discuss it. So what we are going to do is we are going to create a restaurant robot application. Okay, restaurant robot application. So you know what is happening in a restaurant, right? So these are the things happening in the restaurant. So we will be first powering on the robot. Okay, and after powering on the robot, it will be always checking for a customer call. Okay, like whether it is the whether the customer is calling the robot or not. Okay, that is the first thing it will be doing. If it is calling, then it will be navigating to the table. Okay, so if the customer calling from 8th table, then it will be going to 8, obviously, right? And if the robot reach successfully, then it will be taking order from the customer. Okay, and if the order is successful, it will be going to the delivery area or kitchen if the order has been confirmed or failed. Okay, so based on the status of the order, it will be go to the delivery area for taking the food, or it will be going to the kitchen if the order is failing. Okay, and if the after taking the order, it will wait, obviously, and if the order is successful, meaning if the order is ready, then the robot will be going to the delivery area, and then it will be taking the food and it will be delivering to the customer. Okay, but if there is any problem with the order, then it will be going to the kitchen to like mention something wrong happened, and then some people will come and talk with the customer. So this application is what we are going to model using the state machine. Okay, so you can imagine what are the things that we can do with statement. This is a simple example. Sorry, this is a simple example that we can orchestrate using the state machine. So just think about other application. If you work with drones or mobile robot, whatever it is, or if you are working on a robotic challenge, there are set of tasks that we need to accomplish. Okay, so all these tasks we can orchestrate using state machine. Okay, so one of the technique to orchestrate these set of tasks is state machine, and the another one is that I can show you that the behavior trees. Okay, behavior trees. So that is what we are using in ROS2 navigation. It's again almost the same logic as state machine, but it is having much better capabilities. But again, compared to state machine, it is bit harder. Okay, it's bit harder. State machine are like very easy to implement. Okay, so this is what we are going to see, guys. So let's see the code, and then we can also check the implementation and the introspection graph, so you will get an idea first. So we have a code here. Okay, I already implemented the code. So this is the Python code. So we are going to see what is happening in the code. Okay, what is happening in the code, or how can we implement an application. Okay, like this is simply logic. It's even if you see the length of the code, it may have like 166 line of code, but it's very simple. Okay, very simple in sense, like we are simply creating the states, and then we are starting it and giving the transition, all this stuff. That is what we are going to see in this example. Okay, so from this graph you will get an understanding, like we are giving a user input, maybe some state, some input to power on. So power on will be listening to one of the input from the user. So if it get the input, it will be power on, and if the power on is successful, it will be going to a button state. So button state basically indicates that whether it get a call from the customer. Okay, so imagine if there is a button in all the tables. Imagine there are 8 tables and there is a button. Okay, so based on the button state, it will be navigating to the customer table. So if the button state is succeeded, it will be going to the customer table. Okay, and if the button state is there is 2 other states, that's preempted and aborted, so it will be ending that. But if it is successful, we will get back to the preempt and abort. Maybe we can first traverse to the succeed path. Okay, so if it is successful, it will be going to another state called go to customer table. Okay, so what is go to customer table? The robot is in some home position. Okay, whenever it get a button state, it will be going to a point in the map. Okay, it will be going to the point, so that point corresponding to the customer table. Okay, so it will be going to the customer table, and there are different outcomes for that, like whether the robot reaches the customer table or whether it is fail. Okay, so this customer table, if it is successful or aborted, preempted, it will be going to this block. Okay, so in this block, or we can call this as container. Okay, set of, which is having set of task. So what is happening here? If it is succeeded, then it will be going to the order confirmation. Okay, order confirmation, and if that is succeeded, then it, you can see this succeeded block, right? Then it will be going to the delivery area. Okay, so like the customer actually placed the order, and if that is successful and the confirmation is successful, then it will be going to the delivery area, and then yeah, so it will be going to the delivery area, and then it will be it will be like going to the SM route that I can discuss. But what about failure? Like if the order confirmation is failing, then it will be going to the kitchen, and the robot will be speaking to some people in the kitchen, and they will be going to the person will be going to the delivery area, and he will be involving. Okay, so just want to see, like here I think he implemented up to the delivery area thing. You can see here. We can run the program and see what is happening. Okay, so just want to show you like a sequence of tasks, like power on, then getting the call from the customer, then go to the customer table, and waiting for the confirmation, and if the order confirmation is succeeded, it will be going to the delivery area to pick the food, something like that. Okay, so this is what's simply happening. And if the button state is failing, it will be like ending the task. So SM root will be the slash SM root, means it will be ending everything. Okay, so if the robot go to the delivery area, even if it is succeeded or aborted or preempted, it will be like ending the state machine. Okay, so this much of task is only mentioned in the state machine. Okay, so now I think we can simply check the code to get an understanding. So what is happening in the code? Okay, so that is what we are going to see, or maybe I can run it, and then after getting an idea, you guys can I mean we can discuss. Okay, so what I'm doing is, in order to run this code, we need a delivery robot setup, or like restaurant robot setup, right? So we are using Turtlebot. Okay, Turtlebot simulation. So like if you start the Turtlebot, you can see a world with different blocks, right? So we can mimic, we can say this is very similar to a cafeteria. Like there are tables, so there are 9 tables, right? And we are starting the navigation. Okay, navigation. So yesterday I mentioned that the navigation stack is based on ActionLib. Okay, navigation stack is based on ActionLib, and I have shown you some demos as well. Like what is happening with the ROS navigation? If you give a 2D navigation goal, the robot is trying to reach that goal. Okay, but if we are giving another goal before finishing the first goal, what the robot does is that it will be cancelling or preempting the existing goal and try to reach the new goal. So I can show you that. So I'm giving a goal position. Okay, so robot is going to the first goal, but if I'm giving another goal, it is actually cancelling the first goal. Okay, and if I'm giving a third goal, again it is cancelling and trying to reach the third goal. So what is happening is that always cancel the existing task and execute the latest one. Okay, so this is what ActionLib gives to us. And if you compare ActionLib or ActionLib to ROS service, what ROS service does is that it will take a request, and it will be the client has to wait until the task is finished. Okay, then only we can give a next request. But ActionLib is not like that. Okay, so I mentioned that ROS navigation stack is actually an ActionLib server or action server, so that we can give the request. Okay, so what we are seeing is we are using RVs and we are giving a request, right? So here RVs is acting as a action client. Okay, action client. So ROS is giving a request, okay, a navigation request, and it will be receiving in the ROS navigation move base, and then it will be moving the robot. Okay, so there is an action lib client inside this code that we are running. I will be discussing that. So now we are running the state machine code, and you can see it is powering on the robot. Then the state machine transition from power on to button state, then button state successful, go to customer table, go to customer table is aborted, then order confirmation, starting the order confirmation process, then order confirmation succeeded, go to delivery food, and then go to delivery food is aborted. I mean, it's switching with the task, right? You can able to see. So it's very difficult to decode from the terminal messages, right? So let's start with the smash viewer. So you can see a command called ROS run smash viewer.py. This is what we are using to introspect the state machine. So this is a very convenient tool for debugging the state machine, and also to get the visualization of the state machine. So this is having some more state that we have seen in the chapter. The actual code is having some more state, I guess. You can see here. Yeah, so here we go, like the power on, button state, then go to customer table, and it is going to the customer table, and if it is successful, it's waiting for the order confirmation, and if the order confirmation is successful, it will be going to the delivery area, and if the delivery area is successful, it will be delivering food. Okay, and if the delivering food is successful, it will be going to the home position, and then again the loop continues. It will be waiting for the button state. So that is how the loops work. But in the chapter, I think he only like mentioned the basic up to the delivery area only he mentioned, but you can easily see the actual state. So let's start with the power on, then button state. So if anyone press a button in the table, the robot go to the customer table. Okay, and if it is successful, it will be waiting for the confirmation. So currently it is waiting for the confirmation. The green indicates that this is what running, and now it's got a successful message, and go to delivery area and delivering food. So you may be wondering what is happening in the background. So you can see on each state the robot is moving to some place. You can see here. So go to home is what currently going. So the robot command to go to home position, and now we got go to customer table. So it actually got a command to go to here. You can see here. Basically what is happening is that when the robot reaches each state, that state actually giving a goal position. Okay, so corresponding to that goal position, robot is actually moving. Okay, there are some problem with this turtleboard simulation, meaning I have changed the path planner and also it is not very stable, but I think you got my point. Like if the real robot or the simulator robot is ready, and if you run this application, you can easily see the robot is going from one state to another, and this is like this state now go to delivery area, which is like it will be going to one position in the map. Okay, then the next thing is delivering the food, then it will be going to home. Okay, so maybe what I can do is I can show you the code for better understanding. So I hope you got an idea. This is a state machine example. So let's walk through the code. Okay, So again, as per the first example, we have seen how to create a state, right? So you can see the power on robot state. Okay, power on robot state is here. Then the button state. Okay, button state. So this is the state that is waiting for the user input. So currently it is like giving a fixed value. Like when the button state trigger, it will be giving I mean, based on the button state, I think, let me see. Yeah, I think if the button state trigger, it will be giving successful. Okay. So this is a button state, then order confirmation state. So inside this state, you can include anything. Like you can put your code inside this execute, because execute function is what running when this state trigger. Okay, whenever the robot reaches this state, it will be executing this function automatically and returns these outcomes. Okay, so you can see here if the user confirmation is 1, meaning like if the button state is actually successful, it will be coming to order confirmation, and that is what we are getting, like this will be actually 1. Okay, user confirmation, and if the user confirmation is 1, then it will be printing confirmation of the order succeeding, and this is the speak out state. Then what? So these are the states that we have modeled, and now it's a time to create the state machine and adding all these states into it. Okay, but there is one thing to do. So here if the robot there are some states like go home, then go near to the table, all this stuff, right? So in order to do this, we need an action client. Okay, action client. So then only we can send the position in the map. Okay, then only robot can reach that position. Okay, so what we are doing here is we are actually creating a list of points. Okay, so for example, we are actually storing the points on the map. For example, the table is on the waypoint 0. That is the first point is the table, corresponding to table. Then delivery area is this point, xy theta. Okay, then kitchen is this point, home is this point. So whenever go home state is triggering, it will be going to this point. Whenever kitchen is triggering, it will be going to this point. Okay, it's very easy. And yeah, so that is what we can see here. So in for corresponding to each location, here they are created a move based goal. So if you want to go to home, then you can simply send this goal. Okay, so this is what the action client about. Okay, so they created a list of goals. So whenever we need to move to table, we can simply take the goal from this. Okay, nav state, that is what the list is. We can simply take the nav state. For example, nav state 0 corresponding to table, nav state 1 corresponding to delivery area, and go on. Okay, and then here we are creating the state machine. Okay, so we are adding state machine one by one. So one state machine, order confirmation, then we are creating another state machine called SM restaurant. Then with in the restaurant state machine, we are adding the power on, power state, all these state machine. You can see here power on, button state, then the go to customer, go to customer care table, some order confirmation. I mean, we are actually adding all the state machine into it. Okay, so here let me check the speak out. Let me check where is that state machine. The speak out, speak out is here. So basically, like we are adding the state machines, I mean states to the state machine, and also giving the transition. Okay, so for example, if the power on transition is succeeded, okay, it will be going to button state. If the button state is succeeded, it will be going to the customer table. Okay, if the customer table, if it is succeeded, it will be going to order confirmation. Okay, so it will be going like that. And so that is what is I mean, like this application about. And after creating all this state, we are starting the introspection server and then starting the state machine. Okay, so this is what happening in this application. So basically, creating the state machine, adding to the state machine, start the state machine. Okay, so the advantage of doing this is that this kind of application will be very modular, because we are modeling the states using the class, and inside the class we can do whatever we want. Okay, so it's very easy to debug, and moreover it's very easy to visualize. That is the most important part, because when you create a robot application, if you are creating an application using if else condition, it will work. Maybe it can mimic the state machine, but it's very difficult to debug. So we may have to like do the print statement to print what is happening in each block. Okay, but using this, we can easily using the Smash viewer, we can easily visualize the state machine states, and then based on that state, we can we can see what is happening. We can actually decode the state of the entire application. Okay, so that is what I just want to communicate to you guys. So like this is like a real application, and using the state machine you can easily choreograph your application of your robot. Okay, so I think that's it for today. That is what I just want to communicate to you, and the chapter is here. I will be sharing the book, ROS Robotics Project 2nd edition. The code is also in the GitHub. You can try it out. And so that is what I actually intended to discuss in this course. The chapter called State Machine, like how to create application using it. And I also plan to discuss about FlexB, but it seems like it's not well supported now. But Smash is supported in ROS 2 as well. So I think it will be better to discuss only Smash. Okay, so we have seen the latest example is actually the demonstration of like how to handle the navigation using state machine. Okay, it's similar to the manipulation, because if you are working with move it or navigation stack, all are action client, action server, and what we have to write is an action client. Okay, so I think we have discussed most of the chapters in all the chapters in ROS 1. So now it's a time to start with ROS 2. So before starting ROS 2, let me see, I need to take some time. Maybe there are some more people are interested to join to ROS 2. So I'm just planning how to start with ROS 2, maybe take some enrollment for ROS 2, and closing all the other things with the ROS 1 course, and start with the ROS 2. Okay, so ROS 2 again, an equally important part of the RDLP 2.0. I will say the most important part, because what we are trying to learn is that from ROS 1 we are trying to migrate to ROS 2. Okay, so if you start working with ROS 2, then you don't feel like you are a fresher, okay, because you already know ROS 1 and the concepts are almost the same, only the command lines and the APIs are different. So you will feel like you are experienced. Okay, so that is my intention of including ROS 1 in the course. Okay, so you obviously know ROS 2 is going to be the future. So we are planning to like migrating from ROS 1 to ROS 2. So that is what we are going to see next. So I will be announcing the tentative dates. Maybe what I'm planning to do is maybe starting with the basics and then start with some projects to kickstart the ROS 2 program. So let's see, I will be announcing the ROS 2 tentative dates. Yes, so just want to know, if you have any question regarding the state machine that we have discussed today, and yeah, so let me know, guys. Do you have any specific question for the state machine?
Is the state machine integrable with this navigation stack?
Yeah. I
Or
mean, so so this state machine, no, the state machine is actually a ROS node. I mean, like what we are doing is we are integrating the state machine library to a ROS node. So this is a Python ROS node, okay, ROS Py node, and inside that we are actually including the state machine library called Smash, and we can also see how to call the navigation goals from this code. Like we have seen, right, from the RVs we can able to command the robot to go to one position, right? Using the 2D navigation button, you can command the robot to go to one position. So the same thing we can do from a program. So we can give x, y, theta value from the program and the robot will work. Okay, so that is what we are seeing in this example. So you can integrate navigation stack client, then the Smash and ROS Py in a single node. It is possible. Okay. Yes. Is there any other questions? Okay. So I think we can conclude, guys. So so I will be announcing the tentative dates for ROS 2. Okay. And yes, so thanks for attending, guys. So I will be updating you with the dates. Okay. Thank you, everyone. Thank you, everyone. Bye. Bye. Bye.
okay.
Bye.
Bye. Bye.